thrilled to be opening the program, and congratulations to the organization. Seeing so many people is just fantastic. And I'm just going to jump right into the topic. I want to talk to you about how, from Semidynamics, we're helping all the people trying to go into the AI market and how our technology is helping them. And I'm going to be talking about our all-in-one RISC-V compute engine. So many of you may have seen a picture like this. This is what I call an old-style AI architecture. We've seen many SoCs in the market that look somewhat like that. There's a bunch of cores. Of course, everybody in the room wants those cores to be RISC-V, but we know there are other competitors and there are other cores driving the system. And a lot of people put next to that an NPU, a neural processing unit, which is a large amount of maps, little yellow boxes, multiply equivalent units, which the goal is basically to multiply matrices. And then people, understanding the workload, AI workload, say, well, I got to run something else. So, well, I'm going to also add a GPU of some sorts to run what in the language is called activation functions, right? And this architecture is actually quite popular, but it has many problems. First one of all, it's 3 software stacks. So if any of you is trying to think or build a SoC like that, think carefully, because you'll end up with your, hopefully, RISC-V cores, but an NPU from another vendor and a GPU from another vendor. So you'll end up having to mix 3 software stacks. Oh, sorry, too fast. Second is going to go, your software team is going to have a lot of trouble doing DMA intensive programming. You'll be doing DMA copies from yellow to blue, from blue to green, then from green to yellow, and your software team is going to hate you because they have to synchronize all these copies, and it's a mess, right? And copying those things, I see, I'm seeing the 2 slides, okay. So we call that DMA intensive programming. So by doing DMA copies, you actually pay another price, which is high latency, because those copies unfortunately take time. And they take energy and power, because you are copying data from yellow to blue, from blue to green, and so on and so forth. So it's not good, right? Also on the block diagram, you see these black boxes where I put the words cache or SRAM. Doesn't matter which religion you follow, whether you like caches or scratch pads or just local SRAM. You're going to end up with 3 replicated arrays of storage that is costing you PPA, right? So that's actually not good. And it's very difficult to scale these things up. Maybe your NPU vendor that's providing you the IP can scale very well, but maybe your GPU doesn't scale that well, or maybe your cores are not as good as you thought, right? So scaling this thing is actually complicated, right? And I'll try to convince you later with a slide that this is actually, architecture is not AI future-proof, and I'll see if I succeed in convincing you. Instead, what do we propose? We propose merging these 3 things into one, right? We propose that we have the core, right? Obviously RISC-V, we wouldn't be here otherwise, right? And the core is really in control of everything. So the core, attached to the core, we have a vector unit, which has these big F blocks, which are F maps, floating point multiply equivalent units. But also connected to the core, we've extended the RISC-V asset. That's one of the great things that Talista was talking about, this is a greenfield. We can go ahead and add new technology. We've added a bunch of RISC-V instructions to drive a tensor unit, which is composed of a bunch of multiply equivalence units, right? Why is this better? Well, first thing, it's a single software stack. It's RISC-V. It's just RISC-V instructions. So your software team, if you choose this solution, is not going to have to now piece together 3 different architectures, 3 different software layers, right? Second thing, I hope it's obvious from the picture, but I'll say, DMA-free programming. You're not going to be copying data from yellow to blue and from blue to green. No, don't worry. It's all under the core. There's no copies, and therefore, if there are no copies, surprise, it's 0 latency. Your data is inside the core. You're not moving data. No latency, 0 clock. And lower power. You're not wasting energy moving data from one place to another. Now, also, whether you like caches, whether you like scratch pads, I don't care, but that black box on top is going to be 1, and your data is going to be in one place, not in 3. You're not going to waste silicon area replicating copies of the same thing 3 times, right? And it actually makes for really nice scaling, right? once you have this block, making copies of those blocks gives you a very nice scaling, very balanced. So you need more AI compute, no problem. Put more of these, and you'll get a very balanced solution, right? And I'll try to convince you that it is AI future-proof. I have a slide coming up. Now, to be very technical, I wanted to have a block diagram. I like block diagrams, so you'll have to endure. There's the RISC-V core on the left. Connected to the RISC-V core, we have the vector unit. We've talked about this in previous summits. This is the vector unit contains 8, in this, I think it's 16 in this case, floating point multiplier accumulator unit. And the thing we announced last summit was that we also had the tensor unit directly connected with the vector unit. And the point of the diagram, besides impressing you with the nice pictures, is that everything is connected under control of the core, right? That's really the point of the diagram. So, and you know, to give you a glimpse, and we talked about this, you can go to our website and learn more about it. I wanted to show you how this is different from the classic old style AI, right? You can write matrix multiply in exactly 8 RISC-V instructions, right? These, yes, it's complicated, there's lots of letters. I'm not expecting, there's no exam as you come out, but it's really just RISC-V instructions. There's nothing special. You go to manual, it's just a program. You can debug it with your debugger. There's nothing strange about it, right? So I'm not going to go into details, don't worry, right? So I wanted to talk about AI when what our AI customers come to us and say, hey, how are you going to help me solve my AI problems? And we get 3 questions, right? What software stack, that's my time, right? Okay. What software stack do I get with your IP? Can I run your models today? And can I run the future models? And the third question is really interesting because these AI guys keep inventing things, right? So you start your AI design, your SoC design today, it's going to take you 3 years to go to market. How are you protected against the future, right? So let's go, can I scale? Can I scale your solution and your future models, right? So let's talk about the software stack real quick because I'm running out of time. We chose to go with ONNX. ONNX is a standard started by Microsoft. They have this really nice runtime environment, and you can just take ONNX. You can take any training framework, any framework you like, PyTorch, TensorFlow, Keras, you name your favorite. They all export to ONNX. If it runs on ONNX, it runs on Semidynamics AI solution. So we've written what's called an execution provider, which tailors the ONNX execution to our hardware. We've optimized it, and so you can run any model you want on our hardware, right? The next thing we get a question is, well, Red, you say that, can you run LLMs? LLMs are, transformers are the rage these days. Everybody wants to know, hey, can you run transformers and LLMs on your solution? And our answer is yes, right? And today I'll talk about Llama 2, the FP16 version, 7 billion parameter that you can download from Hugging Face yourself, right? So in order to talk about it, we chose, of our tensor units, we chose the small one, the tier 1, the one top tensor unit. We chose, for our vector unit, we chose the V128, which is the 128 intake gigaops, and we put that together, and I wanted to show you a table. It's lots of numbers, but I'll walk you through it. So what happens when you try Llama on our solution, right? Then what is this big table, right? What you can see, these are the operators that make up Llama 2. You can see there's matmul, and then there's a bunch of activations, right? And the first thing we need is run this thing on our solution only on the RISC-V core, and we call that 1x speedup, right? And the first thing we need is analyze it. And, well, probably half the room already knows this, but surprise, when you run these large LLM models, what you get is 99% is matmul and 1% is activations, right? So the first thing that if you've done your computer architecture class, you'll remember Andel's law. What does Andel say? It says, well, optimize matmul. That's where the tensor unit comes in, right? So we run this thing we teach ONNX to only use the T1 tensor unit, and what do you get? First, you get a tremendous speed, right? Because you just apply the 1 tera compute engine to the problem, so you get a speed of 170. Nothing surprising when you put that kind of power, right? And the nice second thing is that now matmul is actually 20% of your execution time, but now activations are 80% of your execution time. So you're somewhat blocked by that, and you're unbalanced, right? You can see the activation, the details there. You can see that concat and scatter ND are sort of dominating. Sigmoid are also important. So what's your next step? You say, well, okay, I fixed my matrix multiply problem. Now, the thing I want to do now is actually apply the vector unit to address those activation functions. And that's the third column that's coming up. What happens when you do that? Well, two nice things happen. First, you get another almost 2.7, 2.8 speed up. So now your speed up has been enormous. Now you're running 1 and 2 at a very respectable speed. But actually a little more technical detail that's actually better, you now have a balanced architecture. By putting everything together, the tensor unit, the vector unit, and the core driving everything, you now have, 55, 45 is not perfect, but I'm actually quite pleased because now you have, according to Andel's law, a very balanced solution that now you can think about scaling. Now you're going to say, well, but maybe that's not fast enough. Maybe I actually want more performance. You put together this one block, how do I scale further if I want more performance from Semidynamics? And our answer to scale the solution is to actually replicate this thing, right? So what we do is we take the block you see on the bottom, right? And we just make multiple copies. How many? Well, I'm going to ask the customers in the room, but my answer is always whatever you want. You tell me the performance you want. We supply you with the IP, and you guys add as many copies as you need in your solution, right? And we see a number of good things there. First, you can share the cache across all these elements and optimize that. As I was saying before, I said, hey, if you replicate the data, you're going to be wasting area and power. Here, you can actually share the cache, right? So when our customers come to us, we say, pick one of our tensor units, pick one of our vector units, and just replicate these engines as many as you need until you hit. And we work with our customers to define what's that performance and how much performance they need and how many of these units they need. Here I put 8, some customers will need 4, some customers will need 32, some customers go crazy and want tons and tons of these units put together. I always, when I show this picture, I always get this question. People sometimes are lost, like, well, I'm lost, he's got all these copies, where is the software running? And actually, many options, right? These are full RISC-V cores, and the beauty of RISC-V is actually those cores are fully capable of booting Linux. They actually have virtual memory, we actually have hypervisor. So, these are very, very capable cores. They're not just tiny, little microcontrollers driving the thing. They're very capable. So you could run Linux on this array of cores and run the ONNX runtime there. But of course, other people say, well, I actually would like to have some main cores, which again, I'll say it again, we all hope these are going to be RISC-V cores, but sometimes they're not, unfortunately. But we're working hard to make them. And you could also run Linux on top and have ONNX actually dispatched to these engines, right? So once again, the answer is whatever the customer wants. You can do a system like that. You can do a system with no main cores. In any case, it's going to be RISC-V. In any case, you're going to be running the ONNX accelerated solution on our thing. Another thing that I want to touch on is future-proofing your solution, right? So those of you in the room that are thinking of building an SoC, it's a lot of money you're going to invest. And when you're going to invest that money, you have to buy IP. And one of the concerns of our customers is, well, how do I know that this IP I'm buying from Semidynamics is going to be useful in the market when I hit the market? And that's actually a very difficult question. And to convince you, I have a very simple argument, but it's very powerful, right? When you think about this all-in-one element, fundamentally it's just instructions. So it's just a RISC-V program. This very complicated hardware that we put so much effort and love to build is driven by a RISC-V core. And going a little bit pedantic, the RISC-V core is a Turing complete machine, right? So it can run any program you guys in the room and the people not in the room can invent. So no matter what they invent, if it has ifs and else's, if it has recursion, that's about it, that's a program. Any program you can express in PyTorch, any program you can express in TensorFlow or in ONNX, if you can express it in ONNX, we will be able to run it. And that's why we say that, we are future-proof. If you buy the other architecture style, you don't know that fixed function, whether it's going to be appropriate or not, for things that none of us in the room know that are coming, right? We don't know what's going to be invented by the AI guys in a year or in 2 years, right? So with a solution like this, your investment is actually safe. What else do I have? Actually, that's my last slide. I'm 3 minutes ahead of time. I was reading the time wrong, but that's perfect. My last slide just summarizes what we said, right? With our solution, you get a very solid software ecosystem running on our solution, which is based on ONNX. It's fully open source. It's open source at RISC-V, so no worries that you'll be locked into a Semidynamic solution. Don't worry. You get ONNX, you can use ONNX. Point two, can I run today's AI models with current IP? Yes, you can run Llama 2. This is the first time we share with the world that, yeah, of course our solution can run an LLM like Llama 2. We have it running in the lab. You can come to the booth and ask all the questions you want about how we run Llama 2, so that actually works fantastically well. And can I run future AI models? And the risk of boring you and repeating myself, yes, because this is a solution with the core driving everything, the vector unit, which is a bunch of RISC-V vector extensions, and the tensor instructions, again, extensions enabled by the openness of RISC-V. You will be able to run today's models and future models, no matter what people invent. So without that, I'm happy to host you at our booth, which is coming out of the main hall. Come visit us, ask any questions you have, ask any details you want. Thank you very much, and let's